Hello, welcome back to the NES Emulator series. Welcome back to episode 4. So in the previous episode we took a bit of time to make the tests nicer. So NES Emulator series, by the way. Yeah, so last time we converted this main method into an actual zig test so that we can do zig build test. And it would actually run the test, see, okay, the first two lines succeed, and then line 3, P is it's supposed to be 26, but it's 24. So now we can really hammer down on the instructions. And I already found what seems to be too good. So we've been using this instruction reference, and then I also found this page which seems very detailed. So you have the instruction, you have the different flags, and when are they set. So let's get started. So it says that on line 3 it sets the LDX, which is E2. So maybe I can find this here. Set if x equals 0, the 0 flag. LDX immediate. So we fetch the byte, and then if CPU.x equals 0, then CPU.flags.0 equals true, which we can, of course, refactor like this. Okay. And the negative set if bit 7 of x is set. So that just means if we think of the byte that represents x, this is the 7th bit, and usually in 2's complement, in the 2's complement way of expressing numbers, this is obviously the sign bit. So the whole number is negative if this bit is set. So what we can do is we set it negative if basically, so we could do smaller 0, but right now the x value is an unsigned 8-bit. So we could transform it, or we could just check the bit. So I would just check the bit, which means we just need to see if the if we end it with 0x80, which means we end it with this very bit. We can also maybe this is more readable. And basically we see if this bit is set. So we end it with this, and if it's not equal to 0, then it should be negative, I think. All right. Let's see. Brilliant, look at this. Line 10, expected PC to be different. Yes. So line 10. what we observe is that oh, we don't print the line. Wait, let me just go ahead and so we execute it here. Where do we print the line? Where was that print? Oh, the print is, I think, in the execute. Print. Yeah, it's in the execute. I think I would put it out of here, and I think it's supposed to be printed, yeah, outside of this, because yeah, but it doesn't show. Maybe we should print it before checking all of these values so that we can actually see what the line was. Print is not marked public. It doesn't need to be inline. Yes, brilliant. So now we can actually see this is the line we expected. Here's the error. Line 10. Somehow we jumped to 4, but it expected it to jump here. Line 10. Line 10 is a no-op operation. Oh, but probably here. So branch if carry set. So this doesn't affect any flags. This is actually brilliant. I think I'm just gonna. I will definitely also put this in the references. If the carry flag is set, then add the relative displacement of the program counter. Then add the relative displacement to the program counter. Oh, okay. I should add it to the program counter, but what I do is, so this should be plus equals, maybe like this. So for those of you who don't know this, I mentioned it before, I think, but this is the modular plus equals. So this is defined to wrap, which I think it's just safer to use. Absolutely brilliant. Now we see unimplemented 90. And this is really, in my opinion, whatever you program, be it web development, you know, emulator, whatever. I think one of the most important things in programming is that you find some sort of feedback loop, that you can really get into this very quick. You see where the bug is. You don't even have to check the input. It just tells you what the next mistake is. So we have $90, which is branch if carry clear. This is the same as the previous one, but just the set version, I think. Okay. Branch if carry clear. I'm thinking whether I should keep the order here. Actually, I think I should not care about the order, because I should just, you know, put them together however I like, because anyway Zig will tell me if I don't do it exhaustively. So this should be the same code. And by the way, later we can also see if it's faster, you know. Usually switch case, it might implement it as some sort of jump table. Because what you don't want to do is, if it really does like if else, if it produces like a jump for each of these instructions, then it might take a very long time for the decode part. But if it's some sort of smart jump table, or maybe we make an array of function pointers or something like this later, then it should, in theory, just be a lookup and then jump to the right code. Okay, so here we say if it is it like this or like this in Zig? Yes. Next instruction, A9. This should be A9. Okay, I should be careful not to cover where you can see my face. A9. So this is the load accumulator immediate, which loads the accumulator. Which should be the same as the other immediate things. Okay, don't forget random punctuation. Okay. cpu.a equals fetch byte. And we should also set the flags. So 0 flag if a equals 0. cpu.flags.0 equals cpu.a equals 0. And I think this is also missing here. And here it is negative. Okay, so this should all be the same code. Looks good, looks good. F0. So this should be here. We don't know what it is. F0 branch if equal, if the 0 flag is set, then add the relative displacement. Okay. So this is this. Looks like barbecue or something to me. So we had other branching stuff here. So let's just do it here. branch if equal if 0. Okay, so in assembly usually if you want to know if two values are equal, you can just subtract them, and then if the 0 flag is set, then you know they were equal. That's why it's branch if equal, and we talk about the 0 flag. 0. So if it is, then I think maybe there's a branch if not equal, and this is D0. D0. Branch not equal BCS. Branch equal. Branch not equal. And I really wonder, like, okay, we have a lot of duplicated code. I mean, at some point you can refactor it if you want to. But on the other hand, like, it is 256 instructions. It's not 1,000 instructions. So it might be just more readable to just be able to jump directly. Okay, I have this instruction. These are the steps. Instead of, okay, it calls load immediate and it puts in the register and it calls 3 functions. So there's pros and cons. I like this style of just having a big switch case. Yeah. '85. Look at us making progress. 0 page. This is STA store accumulator. Okay. What was it? 85, right? Yeah. 86, 85, 0x 85 store accumulator. Oops. Okay, where do we put it? Let's just put it here. Where do we store it? M equals A stores the content of the accumulator into memory. Into memory where? It reads it immediately, or? Zero page. I think I can just look at here, store A. Okay, so this says store A and this says 1, so it offsets the 0 page by this number. So we need to read a byte. Okay, so we read 1 byte. Where's my fetch byte? And then we store it at this address. So we write byte address equals bitcast so I think we need to cast it as a U16 and then we have the address. Oh, can also do this. Okay. And we have memory, we have address, and we have CPU.a. And does it affect any registers? No, it does not. $24. Or not really 24, but 2 times 16 plus 4. Something serial bit test. Bit test. This instruction is used to test if one or more bits are set in a target memory location. The mask pattern in A is ended with the value in memory to set or clear the 0 flag. But the result is not kept. Bits 7 and 6 of the value from memory are copied into the N and V flags. So overflow and negative. Okay. This seems a little bit more involved, but we can do it. Let's just put it below this in the same order. What we can also do is okay. So we need to read from memory. This instruction is used to test if one or more bits are set in a target memory location. The mask pattern in A, okay, so we need A, is ended with the value in memory. In memory where? Okay, so memory, okay, so it reads, okay, so address, we have to do the same kind of nonsense. So we have the address in memory. We read from that address. Read byte memory address. Const byte from memory. Let's just be super verbose. And what is the next step? The mask pattern in A. So we end A with this value. Okay. Byte from memory and CPU.a. with the value in memory to set or clear the 0 flag. The mask pattern in A, what? So A and M, okay, M and N. N equals this, V equals this, and set if the result, Okay, so this is the ended value, and then we do CPU dot flags dot 0 equals ended value is 0, and then we need to read the 6 and 7 byte from the value and set the overflow. And okay, so flags dot overflow equals ended value, and so this should be the 6th flag. So this should be this one. No, this is the 6th flag. 0 1, yeah. 0 1 da, da, da. And then let's see, overflow and negative. If this is 1, yeah. Okay, this may be correct. I mean, maybe this doesn't need to be its own line. Ooh, they have the same length. Nice. This may or may not work. Finally, a logic bug. Okay, so line 39 expected P. Okay, so this is this, right? 39. The bit. Okay. Okay, again, we end these. Okay, this is fine. The negative flag is set with the 7th bit, so 0. Negative flag is the 7th, right? I mean, the last one. 1, 2. Okay, no, it's the 7 when you start with okay, 65 for 2 flags. I can never remember this stuff. Yeah, negative is the 7th flag. So if you start with 0, 1, 2, 3, 4, 5, 6, 7. So we have the 7th bit, we end it, so we mask out this bit. And if the value, oh no, greater 0, sorry. The value wouldn't be 1, it would be this exact value, so we can also do not equal 0. Okay. It's been a while since I masked bit and such things. 7 times 16. By the way, does anyone know how do you pronounce? Like, is there a cool way to pronounce hexadecimal? Like, I can say 70, okay, 7 times 10, but it's in reality 7 times 16. So 7, yeah, I don't know. Anyway. Branch if overflow set. Okay. Let's just put it right after the other branch stuff. Branch not equals branch if overflow set. Then I guess there's also the branch branch if overflow cleared, of course, which is at 50. Branch if overflow cleared. And we also put it next to the branch stuff. Yes. Maybe we can do a little branches. And this should be the same thing with this being cleared. Let's just see other branch instructions. So branch if carry cleared, branch if carry set. I think we have this. Branch if equal, bit test. Branch if minus, there we go. Let's do this as well. Branch if minus. It's a little bit crude to copy paste so much. Negative. Branch. Branch if positive. This is the opposite. So branch if positive is here. Okay. All right. Expected found on line 62. Wow. Like, look at this. We went through all these instructions until line 62 and then it didn't work. So this is something I think we implemented before, but we probably didn't care about the flags. No. Didn't I put a combined 2 bytes? if I have a combine bytes, I should also have a split bytes, which has a value U16. Can I do this? And then so let's see. Address. Yeah, but how do I return it? I think. Let's do something silly like this. Struct lower, higher. Okay. It returns 2 bytes. And I think we can also do this. So we can do const 2 bytes equals CPU dot split by bytes so we push the higher one first, right? How is it? So this, for instance, no, we should push the, I really don't know which one to push first. Is it the same line? Yeah. No. 62 PC expected found. Okay, so this is a return subroutine. This means we return to whatever is on the stack, which comes from a jump subroutine, I think. And it wants to return to C5 F5. C5 F5 jump. we return subroutine after, wait, pull processor status. We don't use PLP, I think. So we have a jump subroutine here. Okay. Yes. It expects. Yeah, that makes sense. We are here at C5FD, and we jump, we call a function here. Whatever, we execute the function, you see here, C7, and then here we return from the function. That means we should really be so I think return subroutine doesn't work, obviously. It pulls 2 bytes. So return sub, where is it? RTS, return from subroutine. Why is it not RFS? RTS, return subroutine. Stack 6502 little Indian. Okay. So in the jump subroutine, we load up 2 bytes. Okay, let's go through this we load up the lower byte first and then the higher byte. So jump subroutine, yeah, fetch 2 bytes already combines first, second. Which means we should push, I think, first the lower and then the higher. And when we pull it, really also return subroutine should just be next to jump subroutine. Otherwise, okay. Yeah, it should be in the same. So when we put lower higher, we should also pull lower higher. Maybe this was the mistake. No, still 62. So first of all, it's the wrong order. I would understand if it's C5FE, but it's, so it doesn't work like this. So maybe it is like this. Okay. And the previous one, no op. Maybe I'm doing something wrong. Return. It pulls the program counter -1 from the stack. -1. Okay. Jump to jump subroutine. I cannot remember what. Jump subroutine. Instruction pushes the address -1 of the return pointer to the stack. So I think the jump subroutine should split the bytes PC -1. This is somehow better. Maybe, wait, the no op. No, no op happens very often. Okay, it pulls the program counter -1 from the stack. Okay. I think what would have been cool is if in the log file they put like, or maybe this is this stuff? No. Okay, this is something else, but it would be cool if they put not just the stack pointer, but what's actually on the stack in the thing, because then you would really be sure whether you push things onto the stack correctly. Return from subroutine. Let's just ask AI, whatever. Implement return from subroutine in the 6502. Give a very minimal example. Okay. Okay. So it wait, but we're doing this when we pull the byte. We do, okay, don't need to do this. We are sure we want this. Yes, we make stack pointer +1. We go to this address plus the stack pointer and stack start, and okay, and when we push, we should do the opposite. Yeah, okay, that all makes sense to me. So it pops the low byte, then it pops the high byte, exactly how we do here. No. Okay, let's just actually rename this so I don't get brain damage. Pop. Okay. So we pop the low byte, we pop the high byte, we combine it, which means we take the high one, we shift it left, and let's just do OR equals, it doesn't matter. Does it matter? Okay. And then we increment PC. Okay, but this increment PC happens each time anyway when we fetch byte. Yeah, but this is definitely the wrong order. Okay. Okay. Wow. This provides a lot of... I don't need all this fluff. Yeah, jump subroutine. Let's see. Jump subroutine should do PC +1. But this is still the wrong order, because this should still be flipped. So push high, push low. Okay. I think now we tried like all the combinations. Okay, this is almost it. This is 1 byte off. So I think the high and low is not. It's just... I really don't know. Let's just keep going for a bit. Let's see what happens if I do this. Then I get all the way to, wow. Opcode 8. Which is 71. PHP. Wow, there's a PHP instruction. Watch out, web developers. You think PHP was only for web? No, it's for 6502. Already had PHP. Push processor status. Nice. This is a very important instruction. PHP. Pushes a copy of the status flags onto the stack. Yes. Push byte CPU. Why do I need the CPU? Oh yeah, because I need the stack pointer. Push byte. Oh, push byte is kind of an immediate thing, isn't it? It writes the byte from memory. No, sorry, what am I saying? So this should be CPU flags. What is that method called? Status register is okay. This might be as simple as this. $68. Okay, let's do a few more. I think pull accumulator pulls. Okay, this is 68. 6.8. Let's go. Pull accumulator. Yeah, we just put it here. Pulls an 8-bit value from the stack and into the accumulator. Okay. CPU dot A equals pop CPU memory. Let's go. It sets the 0 flag. 0 equals CPU.A is 0. And it sets the negative flag if the 7th bit of A is set, obviously. So CPU.flags.negative equals CPU.A. Okay. negative equals, yeah. Line 73. Line 73. Expected A to be 7F, but it is 6F. Wow. Compare. Oh, this is end, yeah. So where does the 7F come from? 7F. Okay, so PLA did not work. Okay. Okay, but that's very hard to debug because we're pulling again. This could be very much improved, this testing, if it showed, like, I don't know, given the stack pointer here is the five top things on the stack or whatever, or the top thing on the stack, because then you could see where you went wrong. Because here we are pulling something from the stack and we received the wrong thing. So last time we pushed it, it was actually wrong. Wait, so we have 6F here. We push 6F, which clearly gets we do compare this, no? Yeah, we compare it to this, to P. And this is 6F. So this is correct. And then we pull it. But it becomes 7F. Oh, wait. Huh? PLA. I think there's just something I don't understand. PLA. Show me does it include the Okay. Mm-hmm. Oh, what does it do here? Clear bit 4 explicitly for PHP. Okay, that would be nice if I could have known this, but okay. Um, 0b. Which flag? B flag. 0, 1, 2, 3, 4. Okay. No. The other way. Sorry. We want to clear, we want to mask that bit. So, yeah. Push processor status. Also, when we push it, we clear this. Okay. This makes sense. This makes sense. Mm-hmm. Okay. Expected 7F. So we have 6F. So what is the difference between 6F and 7F? So this is 6 and this is 7. So the first bit is somehow set. So here okay. Here we have the status is 6F. I did it the wrong way, but anyway. It's 6F. This bytes is in the status register. And we PHP this thing, which means we clear the fourth bit. It is clear. Okay. So we PHP, then 6F. Okay. Then we do PLA. Okay, we can get this PLA. Pull accumulator pulls an 8-bit value into the accumulator, yeah. And this is before. And somehow this gets 7F. So this bit here is set. So maybe it should be explicitly set and not cleared. Where's OR? I mean, this will work, I think, but to do no idea. All right, we got farther. We have some debt that we accumulated. And okay, this is an easy one. This is 29. 29. Logical end. Nice. Yeah, after a bit, whatever. A logical end is performed bit by bit on the accumulator contents using the contents of a byte of memory. A byte of memory. Okay, so we read a byte. Read byte. No, fetch byte. But we don't need any of the casting thing. So we fetch a byte and we do cpo.a and this, and where do we store it? Bit for bit. Okay. Oh, so it is this thing, I think. And then we have the usual thing. We have this thing. So if this is 0 and if negative, okay. C9. Okay. C9 is compare. Compare. This just sets flags. Yes, very easy. This comes after LDA or whatever. Compare. And it precisely sets 3 flags. So it sets carry, if a is greater equals to memory. So first we need to fetch a byte. We fetch a byte from memory, and if a is greater or equals than the value, I think. No, what we are implementing right now is compare C9, which should be an immediate thing, I think. Compare. Okay, so we don't. Yeah, we fetch a byte. Yeah. So it should be immediate value. Zero flag is if they are the same. And negative flag is if of the result. Yeah. A minus M. Let's just do this. It doesn't actually, I think, matter. $48. Okay. Implied. What? Implied push accumulator PHA. So where's PHP? 48. Let's do it next to PHP. Pushes a copy of the accumulator onto the stack. Yes. Okay. $28. So maybe this will be the last one for today. Because when you do enough of them, you get a little bit dizzy. Pull processor status. So let's also do this just after these two. Top of stack. Well, let's just call it, we always called it value. And then we actually need another helper, which we need to set status register from U8 or something. CPU dot flags equals and then we want to make sure that CPU dot flags dot always 1 is equal to true. PLP. Okay. Yeah. Let's see if this works. I did something wrong here. Okay, so look at this. We are at line 104. This was a little bit my goal for today, to reach over 100 lines. So as I said, apart from the stack that we don't see what's on the stack, all the other things like the registers, we know that the first 100 lines of this log file already run through. And in my experience, like, we grind a little bit more, and then all of a sudden I expect it to jump, like do bigger and bigger jumps from like 100 to 1,000 or something, because it's just less likely to encounter not implemented ones or to have bugs and stuff like this, and there are lots of repeats. So yeah, this was a very fun episode, because we had all the things in place and we like look at the progress that we made. We basically implemented 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 new instructions in one video. It's a very nice number. And yeah, if you find a bug, or if you notice a bug while watching, like, feel free to either just feel free to you know, submit a pull request, or just write a comment and I'll fix it. Let's end the episode by making a little commit. Okay. This should be episode 4. Hello. Okay. I think my shift was, caps lock was activated or something. Okay, so implement 16 new instructions. Okay. All right. Thank you so much for watching, and see you next time. Bye.